mean two vectors are unique. Is it clear? Thank you so much. So once we are talking about orthogonal, mean that the two vectors are orthogonal. In this situation, we are talking about bunch of the signals or too many vectors. For example, Q1, Q2, Q3. So these three dots are showing some kind of continuity and number of signals. So the definition of orthogonal, that two vectors are orthogonal once you are considering the first vector, this one, okay, transposed to the other vector and giving you an output equivalent to 0. For example, two signals, okay, two sound signals are mingling up with one another. You cannot, okay, hear if both are having different signal words are different mingling up, so you cannot, you say please keep quiet, I want to listen something, even you say in your home. So the problem is that two vectors are mingling up, so output is what? Not a unique. Output is not a unique. So you say it's 0 only if and only if that I different than j. This different than j. However, you will get some kind of unique signal. Okay? Only and only in case unique means one, binary. Somewhere in the definition bag we studied about the binary. So if and only if I equivalent to j, then you will get this concept. That your two vectors are orthogonal.
The Gram-Schmidt process is used to transfer a set of linear independent vectors into a set of orthonormal vectors forming an orthonormal basis. It allows us to check whether vectors in a set are linearly independent.
Anyone like to explain it? What is Hamza?
Yes, sir.
What he said in this statement?
सर मतलब चेक करता है कि जो एक सेट में से वेक्टर्स हैं वो आपस में लीनियरली डिपेंडेंट हैं या इंडिपेंडेंट हैं।
अगर वो इंडिपेंडेंट है उनको कन्वर्ट करता है सर
ऑर्थोनॉर्मल बेसिस में कन्वर्ट करता है लीनियर इंडिपेंडेंट वेक्टर्स को ऑर्थोनॉर्मल।
हमें इस बात की इजाजत है कि हम चेक करें।
Okay, any example? Last time I talked too much about the Vipsha singing along with the musical instrument.
Yes, sir.
For example, suppose there are two vectors. Simplification, in reality there are too many vectors, but let's suppose two vectors. One is the Habibsa singing or lyrics and other is the musical instrumental sounds, just suppose. So both are linearly independent. And in this Gram-Schmidt process, we made these linearly independent vectors into form of orthonormal vectors. Please pay attention. The concept of this orthonormal vector is to keep the uniqueness. Why uniqueness? Because if we are talking about the two signals, so lyrics or some kind of musical instrument, it's not a big problem, but still you are getting some kind of mixed sound. However, in actual digital communications, for example, there are many students sitting with mobile phones. All of you are getting some call, and the frequency, each one vector or a kind of a signal is receiving by your mobile phone is not fetching the other mobile phone data or other mobile phone frequency. So each mobile is keeping its signal strength in form of orthonormal. kind of a unique frequency. If we do not make the vectors orthonormal, then unique all the too much noise. You will see too many frequencies buzzing around us, and we cannot hear or we cannot listen clearly Danish or Suleiman or Saud talk clearly. You can say it's just kind of a unwanted noise or some kind of mixing of too much. So though each of you maybe or some of your fellows at far long distance is talking very loud and clear, but due to mixing of the frequencies, you will not hear them in a clear sense with some unique manner. So this is the theme of this. So if we, of course, I would like to explain it to. So can you please read it out?
Yes, sir. In digital communication, we apply input as binary bits, which are converted into symbols and waveforms by a digital modulator. These waveforms should be unique and different from each other, so we can easily identify what symbol bit is transmitted. To make them unique, we apply Gram-Schmidt orthogonalization process.
Okay, got it. The same thing. Okay, so uniqueness. Though, of course, if some of your brother or parents are talking with you, this is just one scenario. Instead, simple, I'm using two signals, but if some other of your close relative is talking with you, of course, his talk is linearly independent, does not belong to other ones. Does not belong to other Danish class fellows, so linearly independent. But to keep it unique, we need to apply the orthogonalization process with the help of Gram-Schmidt formulae. Last time I tried to explain, but I was stuck somewhere, so I revisited, and today inshallah I will explain. So this Gram-Schmidt process, Zuresh, can you please read it out?
Gram-Schmidt is also known as the Qr Decomposition. It's the process used to orthogonalize the columns of a matrix. It's usually one of the initial steps in many matrix decomposition. Outside of the LU decomposition and Klausky decomposition, all of the other ones use it. Matrix decompositions are used to solve system of equations, which can be anything really, and the main reason to use the Qr decomposition.
The LU decomposition we already studied. It is but technically it's a factorization of the matrix, and we are factorizing the matrix for various purposes. And one of the basic purposes to use the Qr is also kind of a decomposition process of the matrix. For example, there is some matrix A, we decompose into the form of Q and R. And Q is the orthogonal matrix and R is the upper triangular matrix, but this is some scenario, but we are decomposing this matrix into the two factors. However, till today, we studied in the previous classes some kind of elimination, so decomposition for getting some kind of a solution set. But here, our main target is not to get a solution set. Our main target is to get an orthogonal matrix. So, but how? With the help of Gram-Schmidt process. So, what's the technically? This process look like? For example, you have some color scheme. Of suppose this is some circle of red color. This is A. And it's completely red. If I suppose this vector A, I say just suppose color red. Someone can ask, sir, why we cannot use the union? Why we cannot use the union instead of the intersection? In union, we cannot keep the uniqueness. How? Now, in this situation, you can notice that this is the first one, A is the first one, So B is the second one. So if you are considering the union, then you need to write 1, 2, 3, and in case of intersection, only 2. This is the uniqueness when we maintain. With the help of Qr decomposition or Gram-Schmidt process, we need to maintain the uniqueness. And this uniqueness, don't think this is complex. Okay. Can you please read out, please?
If the condition number is very large, then the matrix is said to be in condition. Practically, such a matrix is almost singular, and the computation of its inverse or solution of a linear system of equations is prone to large numerical errors. A matrix that is not invertible has condition number equal to infinity.
Okay, this is what basically, this is talking when the system is too big. For example, too many people. We are talking about the digital media, the communications, for example, signal of the U-phone. Okay, in this campus, everyone is carrying U-phone, for example, SIM, and we are getting many signals of it. So if the data is too large, no control, no uniqueness, then we are attending some call, we will hear many people are talking, so the system is not well managed, not disciplined one. So it's known as mathematically, in scientific language, it is known as ill condition. So, it's happening because we are dealing the equations, problems in form of a matrix, but the matrix composed from these equations, you can say, usually is a singular matrix. Once we are talking the matrix is a singular, then of course you're familiar, its inverse does not exist. If inverse does not exist, it means system reliability cannot be achieved. You cannot go back, then it means that there is something wrong. In forward direction it is something else, in the reverse direction it is something different. Then its main problem is this, then accuracy is collapsing somewhere on the way.
Yes.
And the computation, this is the thing. So linear system, of course, large numerical errors, errors. Somewhere your communication will be hanged, or you can say the sentences will be broken, or you will not listen clearly. So the not invertible has a condition. Once the matrix is, you can say, not invertible. In start of the class, I told you people the unique solution, infinite many solution, or there is some kind of, so infinite many solution are there. This is the situation occurred here. So if we determine the difference between ill condition and the well condition, I just want someone to speak out about this. Ashmi, playing with mobile.
Yes, sir.
This is important. Go attend the call outside. Go.
Not to that, man.
No, sir.
Okay, just read out this.
In mathematics, a condition number is a number representative of the change of an output proportionate to change in the input of a function. For example, if a small change in the input result is a small change in the output, the function produces a small condition number and is said to be well conditioned. Alternatively, if a small change in the input results in a large change in the output, the function produces a large condition number and is defined as ill condition.
This course name is what linear algebra. And I spoke out many times that linear means whatever you are providing at the input, you are getting the same amount at the output. If there is small input, small change,
Input.
I cannot see. Small change in the input, it is giving the small change in the output, means the same kind of change at the output, then you say it's a well condition. It is a well condition. However, big change in the input, output very small, or small change in the output, input, output is a very big, then there is a problem. So you will say it's a ill condition. I think now a little bit of concept. So in order to avoid this, we need to maintain the system. Why this is happening? Because some noise is contaminating in the system on the way. In order to get rid of this noise, we are applying the Gram-Schmidt process. Let's see what's the Gram-Schmidt process. Suppose there are two vectors. First vector is A. This is the neat and clean vector. We do not have any objection with it. Okay? Just if in a complete silence room, Habib Shah is singing, we can hear his lyrics. So we can notice there is no interruption, no noise. Okay? So that's fine. We can say, according to Gram, the orthogonalization matrix, you can say Q is a matrix where you can say Q1, Q2, Qn, mean n number of signals. Okay, in reality there are too many signals. But if, for simplicity purpose, if I say only two signals, one is the Habib Shah singing and other is the instrumental sound, then I will talk about only Q1 and Q2. Okay, Q1 according to the Gram formulae is equivalent to the A and norms of A. Remember here, don't be confused with the norms value. Norms, this is the thing. For example, you are standing some point here A, and there is some another point B, some another point C. So A to B to C. So this A to C is the norm, simple norm. Simple norm, one norm of one. Here are usually mathematical or computing books, you will not see anything here, only norm. Okay? It means you have, for example, 1 plus 1, okay, this is the 2. Are you getting my point? But even there is a negative value, you will consider it a positive, or you can say absolute value. However, if there is a norm of 2, some students, because I am explaining during the presentation, some students said that norm of square. So if you are talking about this norm of 2, this is like this. This is technically what? This is C square, A square plus B square, and you are taking the square root of both sides. So this square root, this square. Remember the square root. I will explain it. Okay? In orthogonal, this square root is carrying a significant importance. So this C. It's also a norm. Okay, shortest distance norm. Are you getting my point? So this situation, sometimes usually 2 is not mentioned, scale is mentioned, but this is a norm. Here, this norm. Okay, shortest distance. So Q1 is expressing in this way. If we say what's the A, basically we don't need to worry. A is the simple matrix, or you can say this vector A is equivalent to the A, capital A.
Yes.
However, if we say about the second, this column, this okay, this Q1 is basically what? This is orthonormal. This is orthonormal. I will explain the concept why it's orthonormal, because it is carrying the square root. Some distance, suppose you are traveling somewhere, or there is a, for example, with the GPS we are observing traffic is moving on the road. If there is a rush, you see the red color on the road. So suppose in reality, yes, you can notice people are traveling or cars are running on the road, but in one box there are 200 or more than tons of mobile phones, okay, are carrying some signal or some kind of a U-phone or some other signal strength. GPS will tell us that some kind of a huge rush is there. Are you getting my point? But this is the problematic thing. This is not the orthonormal. Why? Because there is square root, distance. This distance is almost zero, negligible. So to maintain this distance, to observe this distance, we need to make a system by following the Gram-Schmidt process. But in this Gram-Schmidt process, okay, let me rewrite this. If only again talk, I like to talk about the Abib Shah singing. So this one is equivalent to A mat, okay. We should not worry about the first orthonormal. It can be expressed as this way. However, if there is one another vector, this one, this is B. It is not, you cannot say it's an orthogonal. You know the definition of orthogonal. The orthogonal should be perpendicular. Why? Because if, sorry? Yeah, actually if it is here, if it's at the position of B, then it will affect this A. Why? Because the shadow. Are you getting my point? Shadow. Shadow projection of this, it is signal is propagating and its frequency will detract the signal A. What we want to do, we want to separate it almost at the angle of 90 degree, and we want to kick it to this position that it should work. Okay, okay, thank you so much. Please. So this nearby signal is causing, or you can say, throwing some shadow on this nearby vector. We need to make it at this vertical position. What will happen? It still can affect this vector A, but at very minute position. Are you getting my point or not?
Yes.
So, yeah, almost kind of a negligible thing. So this is the new position of this vector B, and we will label it as capital B. Remember, this vector is the one vector. If there is a one vector, no surrounding effect, or you can say no disturbance to it, then we can say this is both are the same. But in this case, we are shifting it from this position to this position. Then notice that this B not at all equivalent. Small b does not equivalent to the capital B. So the problem is, how we know according to the gram, okay, the Q2, another signal, should be equivalent to this one. But what's the value of B? What's the value of B? This is the problematic thing. We need to determine this value of B, capital B. This formula is given by some Schmidt. And Schmidt said that, of course, this B is, okay, remember this term. Children, please need kind attention. This is kind of error term. Okay, this term, this, because original position is this, we are shifting it to this position. So it's kind of an error. You may say that it should be here perpendicular in order to get the uniqueness. So some kind of an error. Okay, it's not at the right position. So you need to consider this one. And okay, you need to subtract away what? You need to subtract away A transpose B. Okay, A transpose A, and here this one.
Yes.
Now, okay, this is the formula. With the help of one, you will determine the value of B. You need to place it here. You will get the Q2. So Q1 is orthonormal, Q2 is orthonormal. Both are the unique kind of signal. Yes, please.
We can say that the Gram-Schmidt process is basically making the vectors independent.
Yes,
And
indeed.
if the vector B is like more like a dependent on it, so just to make it independent, we use Gram-Schmidt.
Exactly. Okay, let me show this with the help of one example. For example, you are considering some matrix Q, Q1. Q1 is not, you can say, okay, let's make it simple, very simple. 1, 1, 1, 1, 0, 2. This is some kind of a matrix, but remember, you cannot see any square root in this. If there is no square term involved, it means the distance is negligible thing, or you can say it's not kind of orthonormal vector. These vectors are not orthonormal. So every term of this matrix, okay, this complete column should have some term of equivalent amount. For example, maybe kind of square root 2, square root 3, whatever. Okay, I'll explain it how. But this situation is not, you can say these vectors are not orthonormal vectors. So orthonormal vectors, to make these vectors orthonormal, we can categorize. The first one is A, second one is B. So suppose first one is Habib Shah singing lyrics, okay, A, and we can say without any disturbance, without any noise, without any unwanted data, it's equivalent to capital A. So with this we can get the first A norm of A. However, for getting B, I need to mention A transpose B, A transpose A, here A. So what is the value here? Value of A is what? 1, 1, 1. And what is the norm of it? Or you can say this Q1. This Q1 is 1, 1, 1. This is, see, all values are in square root form. Kind of some distance, maintaining the norms. Okay, so what about, okay, this B? B is, okay, we are already familiar. Once we get the B, we will get this Q2.
Yes, sir.
So this, we need to substitute the value of B here. Okay, let me go to the next page. B, okay, this B, 1, 0, 2, okay, remember. So 1, 0, 2 minus A transpose B. A transpose B equivalent to 1, 1, 1. My child, this is A. This is A. Are you getting point?
Yes, sir.
This is A. As I told you in somewhere that this vector is A. Okay? So here this is equivalent to the A. So we will write this A. Is it clear?
Yes, sir.
So what is the value of B? Value of B is 1, 0, 2. So multiply both of them, what you will get? 1, 1, 1, 0, 1, 2, you will get 3. And again, you need to determine this one. Okay, A transpose A. So if you are determining A transpose A, answer is 1, 1, 1, 1, 1, 1, answer is 3. So you need to substitute here 3 in the numerator, 3 in the denominator, at the place of B 102 and here 111. So B equivalent to 102 minus 3 divided by 3, 111. So you will get what?
0
0 minus 1 1. Now you can get the Q2, okay? This Q2 B. So you will get what? Okay, what?
So
Here.
B is there. B norm is
So under root 2 and
under 2.
Yes.
1 by under 2 or 0 minus. So you will minus 1 by 2 or 1 by 0 minus 1 by 2 or 1 by 2.
0. Okay.
Minus 1 by 2 under root 2.
Square root and here Is it clear to all of you?
Yes, sir.
So notice that here square root term. So vector is orthonormal. It is maintaining the norms. It is maintaining some norms. Of course, if there is no norm or zero, you can ask me a question, sir, what's the zero? Then of course it's not a orthonormal. So if there is some value and even if there is a 1, then it will not maintain the norms. Okay, here you can notice it.
Yes.
No norms. So the situation is this: now you have two vectors. Q1 is some kind of a vector 1, 1, 1, 0, 1, 2, and from this vector, from this Q1, some kind of non-orthonormal data. We deduce what? Orthonormal, unique data, okay? So that we can here, digital communication can be done perfectly. Okay, whatever. So Q2 is what? The new one, 1, 1, 1, so 0, minus. So now check out that this Q1 is having non-orthonormal, okay, some kind of a rush routine. You cannot distinguish between the voice, and this Q2 is, by following the Gram-Schmidt process, we are getting a matrix which is having orthonormal vectors. And each vector, this is from Q1, this is Q1 from Danish family, this is Q2 from Salman family, or you can say Habib, okay, both completely different, unique. You can keep the data. See, once I talked about here somewhere the vectors. Okay, this one. Sorry, n mean thousands of, millions of, okay, our number of signals. You need to distinguish between each and every signal. It's just for simplicity purpose, I talked about only the two vectors. So similarly, you can make it, okay, huge, you can categorize or distinguish the huge data. And one more important thing, here I would like to say, in this class, some students were talking about this thing. That inner product. What is the inner product? What is the benefit of inner product? What is the, see, it's very simple. For example, this is some kind of a data, or let me explain it about some kind of a house example, a Russian model. I already explained that hypothesis data, some kind of theta naught, x naught plus theta 1, x1 plus theta 2, x2. So once we are talking about the house, and of course your x naught equivalent to 1, always equivalent to 1, because this is some kind of, it will not change. We are talking about the unit house, then it's been unit house. Okay, one house. We are not talking about the multi number of houses, so one house. So weight is, there is some kind of benchmark value. You can say that if we are talking about one house, it is having some kind of at least one washroom or some kitchen or some room. So maybe you can categorize it that from the biased value, okay, from the biased or intercept value, that its value is starting from the 1 lakh, okay, or you can say 2 lakh, maybe whatsoever. So the basic value, this is the weight. You can say this theta naught is representing some kind of a standard weight, this one. So x1 does not affect it. But if you are talking about this one, theta 1, this is again the weight value. And this weight value is increased or decreased. It's not the intercept value. For x1 is what? Feature of the house area. If house area is little smaller, then of course this value will be smaller. If the house area will be increased, then this theta weight parameter will be increased. So this is another thing. If this one, again the price thing, and it is depending upon the house stories, okay, single story house, double story house, triple story house. So this is representing the stories. If it is a single story house, then the another price. So what? Basically, we are having some two vectors. One vector is representing theta naught, theta 1, theta 2. And the another vector is talking about the x, and this one is representing x naught, x1, x2. This is the weight, okay, standard, okay, the standard, okay, talking about the some unit house. So second weight is representing the area price. So third one is representing about the first story, okay. So what we do, these are the two different vectors. We need to take the inner product of these two vectors. And once we are getting the inner product, we will get this equation. And then inner product is giving the association of each weight corresponding to its each, okay, vector, feature value. So there is this matrix, you can say it is some kind of a weight value for this given. For example, I am speaking out. If this one is carrying my scale of speaking, somewhere slow, somewhere loud, and this is the words, okay, my words, for example, single sentence, short sentence, long sentence. So of course, once first sentence, for example, some of you are, for example, Danish is comparing those somewhere, okay, increasing the page, decreasing the page. So similarly, sentences also vary. Both the things, scale of sound and the sentences, are coupled with one another with the help of inner product. Not in this only sense, okay. There are, for example, even the digital communication. There are too many signals, but some signal is too weak because its weight value is too less. Okay, not scaled up. This is also kind of a problem then. That's why we are, so we here at this place we are taking the inner product, then normalize. This one is the normalized, okay, normalized scale, and then again we multiply this weight value. So here this error can be overcome, okay, can be reduced with the existing, this one, and the benchmark. This is the benchmark signal. Okay, we are normalizing, or we are considering it, okay, overcoming the error, or we are shifting it with respect to this one. And the difference, okay, are subtracted away, and we are getting our required result. I know this is a little bit stupid things I should not teach you, but with linear algebra, if I teach you linear algebra, just okay, this is the elimination, this is the matrix multiplication, this will not help you out if you do not understand the concept. That's why I engaged you people. I thank you people that you come on the stage and you helped out yourself, and then I came to know where the problem is. Okay, truly speaking, everyone is talking about artificial intelligence, data science. This will not helpful. This will not, you can say, useful unless you will not understand the mathematics. No engineering will work out. No engineering, nothing, no computing will work out unless you will not understand the grip of mathematics, so that you can develop each and every application by yourself. You can you can make a model, you can make these tiny algorithms. Otherwise, your degree just only you are copying some data, other people's data, and just make some simple modification. This will not sufficient. No artificial intelligence will work without mathematics. Try to understand. You notice that these tiny simple things of linear algebra can make you a billionaire, okay? All the Facebook, all the Google, the other things are depending upon these. But who cares if you will not? Okay, so